Hello everyone. Let's study simple harmonic motion more comprehensively and more qualitatively in this lecture. Let's first define simple harmonic motion. A body is said to be in simple harmonic motion if it moves to and fro along a straight line about its mean position such that at any point its acceleration is directly proportional to its displacement but opposite in direction and is directed always towards the mean position. So this is the definition of simple harmonic motion. To understand this, let's recall the previous discussion where we considered a particle of certain mass, and this particle was moving between points A and B. Let's call some of the points P and Q, not to get confused with the constants A and B here. So 2 points P and Q, both the mean position O. What is seen is if the particle starts from point O and goes towards point Q, then in this case its displacement will increase. The particle's speed will decrease as the particle goes from point O towards point Q. Its velocity will decrease. At the point Q, it will stop and turn back or return towards point O. When the particle is moving towards point O, its speed will increase. Because of the increased speed, the particle will not stop at point O because speed is increased now. In fact, at the point O, the speed is maximum, because of which it will cross the point O and go towards point P, but the resultant force or the net force or the force on the particle is towards the point O only, because of which the particle crosses point O, its speed will keep on decreasing. Think of a coin being tossed upwards. When we toss a coin upwards, the coin is moving, its velocity will keep on decreasing because the force is opposite to the velocity direction. So here also, since the particle has crossed the point O, the velocity will be in this direction, but the force is towards the center, because of which the particle's velocity will decrease. The point P will stop and it will again go towards point O. Now when the particle is moving towards point O, the force is towards the point O only. Since the velocity and force is the same direction, its velocity will increase or speed will increase. The particle is coming towards point O, its speed will keep on increasing. Once it crosses point O or once it comes very close to point O, it will have maximum speed. Now since the speed is maximum, the particle will not stop here, because of which the particle will cross the point O and go towards point Q. When the particle is going towards point Q, again the force is towards point O only. So here the force is in one direction and velocity is in opposite direction, because of which velocity will decrease. It is this way that the particle will keep on making a simple harmonic motion. That is what is given here, saying that at any point its acceleration is directly proportional to its displacement but opposite in direction, and it is always towards the mean position, which means the force or acceleration is always towards the mean position. Such kind of a motion is called as a simple harmonic motion. Now there are many forms to write simple harmonic motion, but the most common form is the cosine form or sine form, and in this lecture we are dealing only about its displacement, which is about distance. So we can write x of t or y of t as any one function. There are many examples of simple harmonic motion. One example is about the simple pendulum. A simple pendulum will always not be an simple harmonic motion only if the angle made here is small. Only for small angular displacements this motion would be a simple harmonic motion. Otherwise it will be just an oscillatory motion. Keep in mind that simple harmonic motion is a special kind of oscillatory motion, where the oscillatory motion would be called as a simple harmonic motion if it satisfies the conditions given here. So not all oscillatory motions will be simple harmonic motion, but simple harmonic motion means it should satisfy these conditions. So in that regard, a simple pendulum would execute a simple harmonic motion only for small angular displacements. Similarly, if we look at a spring, in this case the spring and the mass is horizontal. Whether it is vertical or horizontal, it would execute oscillatory motion, and even this also, in this case also, it will be a simple harmonic motion. So there are many examples of particles around us which would execute simple harmonic motion. In fact, even when we speak, when we make a sound, when the sound propagates through the particles would execute simple harmonic motion. The idea of simple harmonic motion is very, very important, because most phenomena in nature, most particles in nature would follow simple harmonic motion. That's the reason that the emphasis on this chapter is mostly about simple harmonic motion, because it is so important. It could be because of the motion of the particles when sound propagates through it, or even the particles or molecules in a solid which will oscillate. There are many instances in nature where the particles would execute a simple harmonic motion. Now let's study simple harmonic motion as a projection of a uniform circular motion. To understand this, let's look at a particle moving in a uniform circular motion. As given here, a particle, say of mass m, starts from a given point. Let's assume that the particle starts from point A. The particle moves in this direction, crossing point B, going towards point C, and going towards point D, and back to point A. The particle's motion on the circle is a circular motion or a periodic motion. The particle's motion on the circle is not an oscillatory motion. So what we'll do here is, we'll assume that the particle is starting from point A, where t is equal to 0, and then it is going towards point B with our angular speed of omega, where angular speed is defined as the angle covered by time taken. At some point of time, let's assume that the particle is at a given point P. So the distance between the point O to point B will be called as its radius. We'll call here as some capital A, or we'll call this as some other point because A is already used here. We'll call this as point E. This is angle theta, and distance between point O to point P is called as capital A. Now what we do here is, from the point P we drop two perpendiculars, one onto the x-axis. Let's call this as point M, and one onto the y-axis, and let the point on OB be some M dash. So M or PM and PM dash are perpendiculars dropped onto the x and then y-axis. This point P will have two coordinates. That's called as x and then y, which means distance between O to M is called as x, and distance between O to M dash is called as y. So this x is called as x projection and y is called as y projection. Now let's focus on any one projection. Let's focus at the point or the distance y. When the particle is at point E, then the point's E coordinates are, it will be a comma 0, because point E is on the x-axis, the value of y would be 0. If we look at point B, its coordinates would be 0 comma a, because on the y-axis value of y would be, on the y-axis value of x would be 0. Similarly, the point C's coordinates would be minus a comma 0, and for point B the coordinates are 0 comma minus a because it is in the negative y direction. Let's look at any one coordinate. Let's look at y coordinate alone. When the particle is at point E, the value of y would be 0. As the particle is moving from point E towards point B, y is increasing. So when the particle goes towards point B, y is maximum. So if we look at its projection, if we look at the y projection, that is, if we look at distance on the y-axis, it will increase. So follow this. When the particle is moving along the circle, moving from E to B, the value of y is increasing continuously. So y is increasing as seen by the blue line here. Y is increasing. So y is increasing. When the particle goes towards point B, y is maximum. When the particle goes from point B towards point C, y will decrease. Y will decrease. When the particle comes towards point C, y would be 0. So for one semicircular motion, that is the particle moving from point E to point C, the value of y has increased, it has become maximum, it is again decreased. Similarly, when the particle moves from point C to point D, if we look at the y distance alone, y would increase in the negative direction. It will increase like this. So when the particle is going towards point D, y would increase. When the particle goes towards point D, y is maximum. That is, in this case, minus a. When the particle goes from point D to point E, the value of y would decrease. So what is seen is, if you look at the value of y alone separately, by this straight line, by this point, when the particle goes from point E to point B, y is increasing. When the particle is at point B, y is maximum. When the particle goes from point B to point C, y is decreasing. It goes to 0. When the particle goes from point C to point D, y would increase in the negative direction. When the particle reaches point D, y is maximum. When the particle goes from point D to point E, y is decreasing. Which means we find that for one complete circular motion of the particle, its projection on the y-axis would be a oscillatory motion. It is very clear from here that when the particle moves a complete circular motion, its projection would be an oscillatory motion. So even though the particle is in a circular motion, its projections on x or y can be or will be oscillatory motion. If you plot as a graph here, we're plotting the y displacement versus time. The graph would be something of this kind. The value of y is increasing. When the particle goes to point B, y becomes maximum. When the particle goes from point B towards point C, y is decreasing. So it becomes 0, which means this point corresponds to point C. When the particle goes from point C to point D, y is increasing in the reverse direction. It will again become maximum in the reverse direction. It will again decrease. So for one circular motion of the particle around the circle, its y position would be a oscillatory motion. And if you plot it as a yt graph, it becomes a sine curve, which means this oscillation would be a simple harmonic motion, because we saw earlier that whenever a graph of a function versus time is either of the form of sine or cosine function, it becomes a simple harmonic motion, which means here its y projection is a simple harmonic motion. Similarly, if we look at the particle's x projection on the x-axis, if this is the reference point, this is the x-axis, then when the particle is at point E, x is maximum. When the particle goes towards point B, x will decrease. The point B value of x is 0. When the particle goes towards point C, x will increase. At point C, x is maximum in the reverse direction, opposite direction. So this corresponds to point C. When the particle goes from point C to point D, x is decreasing. At point D, x is 0. When the particle goes from point D to point E, x will increase. Which means even here also, its x projection would be maximum, become 0, again maximum in opposite direction, again become 0, become maximum. So what is seen is, even though the particle moves along a circle, it is a circular motion, but its x projection or its y projection would be a simple harmonic motion. For example, this corresponds to point P. We'll call it as some P dash. This corresponds to point B, we'll call it as B dash. This corresponds to point C, we'll call it C dash. And this corresponds to point D, we'll call it as D dash. Again, this corresponds to point O, we'll call it as E, we'll call it as E dash. So in this case, its y projection would be a simple harmonic motion. Instead of y projection, if you plot the x projection, so its x projection would again be a simple harmonic motion, but starting value of x is 0. It is maximum, not 0, it is maximum, because starting from the point E. In that case, if you plot the graph of x projection versus time, if these are its maximum values, then it is x is maximum, it will decrease, become 0. So this corresponds to point B, I'll call it as B dash. Again, x would increase in the opposite direction. This corresponds to point C dash, and then x would decrease, then again increase. So this is what we get. This would be a cosine curve. So this is the x projection. So the x projection or y projection would be a simple harmonic motion. If you want to find mathematically as to what the value would be, we can look at the triangle OMP. We saw it that the graph would be a simple harmonic motion, but if you want to look at it mathematically, then we can say from triangle OPM, if we look at sine theta, so sine theta from triangle is equal to, it will be PM by OP, but PM would be by OP would be capital A, its radius, which is the maximum displacement. So from this, what we get is, we get y is equal to A into sine theta, but theta is equal to omega into t. Therefore, what we get is, we get y is equal to A sine of omega into t. So this is what we got here also. Whatever we got analytically, this is what we get by equation also, which means the y projection would be a simple harmonic motion. Similarly, from this triangle, if we find cos theta, then cos theta from triangle will be equal to, it is OM by PM. It's not PM, it is be OP, the hypotenuse, by OP. OM is equal to x. So cos theta is equal to x by A. This implies x is equal to A into cos theta, or x is equal to A into cos omega. This is what is the equation for a simple harmonic motion. Interchangeable, that is, if the motion had been started from the point B, it would have been other way around. So don't always by heart that x is of the form cosine or y is sine. Don't by heart this. Just remember that some function of time is always some constant into sine omega t, or a constant into cos omega t. This is what you should learn. Don't by heart y is always a sin omega t, as I told you, because if the motion was taken from some other point, if it's starting from point B, that is, if the reference point was point B, not point A, then it's a different kind of a curve. But what is more important is whether it's starting from point E or point B or point C or point D or from any other point, what is more important is it's always a sine graph or a cosine graph or a sine function or a cosine function.